Welcome back. Today we have an absolutely fascinating explainer lined up for you. We're going to treat this almost like a masterclass, really pulling back the curtain on how we build robot movement entirely from scratch. So we'll be tracing the anatomy of robot motion, starting way back at the abstract physics of dimensions, and then scaling all the way up to the physical mechanics, the actual nuts, bolts, and silicone that bring these amazing machines to life.
So it all begins with a seemingly simple question. How do machines actually learn to move like us? Or, let's be honest, perhaps even better than us? It is a massive, massive conceptual leap to go from just a static piece of metal sitting on a workbench to a dynamic, moving, purposeful robotic entity. How exactly do we bridge that gap?
Well, to set the stakes here, let's take a quick look at how robot motion is controlled in the real world. We've got everything from manual teleoperation and pre-programmed paths all the way up to sensor-based feedback and that cutting-edge autonomous navigation using AI and machine learning. But here is the absolutely crucial takeaway. No matter how advanced that AI is, the actual motion remains deeply, physically tied to the robot's design and mechanics. The software can be totally brilliant, but if the physical hardware can't move properly, well, the robot literally goes nowhere. So here's our roadmap for this explainer. 1. Fundamentals of robot motion. 2. Exploring 1D and 2D motion. 3. Linear, angular, and circular. 4. 3 types of joints. And 5. Rigid and soft links. Okay, let's dive right into Section 1. Fundamentals of robot motion. The core philosophy you really need to grasp right off the bat is that a robot's motion is closely tied to its design, its mechanics, and its intended tasks. A robot's ultimate purpose entirely dictates its mechanics. You wouldn't build a massive, heavy, swinging arm to delicately pick up a single strawberry, right? Understanding these basic physical rules is just so crucial because the job at hand completely defines the very skeleton of the machine we build.
Moving on to Section 2, exploring 1D and 2D motion.
Before a robot can even begin to move, it needs a sort of canvas to move within. On one side, we have 1D motion. This is movement along a single coordinate axis, just a straight line. It's measured by position, displacement, velocity, and acceleration. Think of a car driving on a perfectly straight road, or maybe a ball thrown straight up in the air. Versus 2D motion, which is movement in a plane with two perpendicular axes, x and y. Now this uses those exact same concepts of velocity and displacement, but in both directions simultaneously. Picture a ball thrown at an angle, charting a nice arc through the air, or a bird flying in the sky.
And this image brilliantly illustrates that exact contrast. Up top, we have that 1D straight-line motion represented by the cars moving purely horizontally along one axis, and below that, the 2D projectile motion of a basketball tracing a curved path through the air. So why does this actually matter for robotics? Because accurately measuring and controlling movement across these specific dimensions is what allows engineers to guarantee that a robot will perform its tasks with exact repeatable precision. You basically have to map the math before the machine can move.
That brings us to Section 3, linear, angular, and circular.
Now that we have our dimensional canvas sorted out, let's explore the specific trio of motions that robots can actually execute within those dimensions. I really love this breakdown because it maps the theoretical physics directly to real-world industrial muscle. First up, we have linear motion, also known as translational motion. This is moving in a straight path. It's primarily used for pick-and-place manufacturing operations. The Cartesian robot is the absolute prime example here, moving along the X, Y, and Z axes. Next is angular or rotational motion. That's moving around an axis. This requires serious precision, making it perfect for inserting tiny electronic components into a printed circuit board. The Scara robot is the star of the show for this one. And finally, circular or rotary motion, characterized by a radius and angular acceleration. You'll see this used constantly in high-speed food packaging or welding large pieces, frequently utilizing the incredibly fast Delta robot. Let's look a little closer at those first two machines. On the left is the Cartesian robot. Notice the rigid, straight-line track mechanics. It uses linear actuators to just slide along its axes. Compare that to the Scara robot on the right, which, by the way, stands for Selective Compliance Assembly Robot Arm. You can clearly see how its mechanics rely on pivoting shoulder and elbow joints to rotate and reach different positions in a two-dimensional space. But what's really interesting here is the Delta robot. Just take a look at its distinct design. It has these 3 arms that move in a circular motion around a fixed central point.
This specific mechanical setup is exactly what allows for blisteringly high-speed precision. And that is exactly why this circular motion machine is the undisputed reigning champion of packaging and food processing assembly lines.
All right, moving into Section 4, 3 types of joints.
So now that our robot understands its dimensions and knows how it needs to move, how do we actually connect the pieces to make that happen? Well, we need connective tissue. Selecting the right joint is absolutely crucial for giving the robot the required degree of freedom to perform its task. And engineers primarily rely on 3 main types of joints: prismatic, revolute, and spherical.
First up is the prismatic joint. This is essentially a sliding joint. It allows linear motion in one single direction, along your X, Y, or Z axis. It perfectly supports those linear motions we were just discussing, and you will typically find it in linear actuators like a pneumatic or hydraulic cylinder pushing firmly in a straight line. Next, we have the revolute joint. Actually, think of your own human anatomy for this one. A revolute joint is a rotary joint allowing rotational motion around a single axis. It acts just like a door hinge, or more accurately, like your own shoulder or elbow. These are essential for creating robotic arms, allowing easy assembly of the links while successfully minimizing friction forces.
And finally, the spherical joint. If the revolute joint is a standard hinge, the spherical joint is a ball and socket. It provides rotation around multiple axes at once. This is the key that unlocks complex, multi-directional gripping. So whenever you see a highly flexible robot hand or a gripper manipulating an object from multiple angles, you are watching a spherical joint hard at work.
And that brings us to our final stop, Section 5, rigid and soft links.
Okay, so we have our dimensions, our motion types, and our joints. Now let's explore the actual flesh and bone that will cover our robot's joints and interact with the physical world. The links are the segments between the joints, and they fall into 2 main categories. First, rigid links. These are solid, inflexible, and typically metallic. You use these when you need absolute stability, high precision, and extreme repeatability for highly controlled movements. Contrasting that, we have the fascinating, rapidly growing world of soft links. These are flexible and deformable, usually made of rubber, silicone, or different polymers. They can literally bend and change shape under certain conditions. They're designed to absorb shocks, reduce the risk of damage, and adapt their shape to interact safely with very delicate objects or completely unpredictable environments.
And that brings us to the end of our anatomical build. We've gone all the way from the abstract concepts of 1D and 2D math, right through the mechanical joints, all the way down to the gripping of a fragile egg. It really makes you wonder, as these flexible, deformable, soft robotics continue to evolve alongside highly precise AI, what seemingly impossible, delicate tasks will robots conquer next in our daily lives? Definitely something to think about.